Hi everyone. Today we are going to go over the last of the three rock types, metamorphic rocks. So we are going to go over metamorphism and how rock actually changes from a protolith to a metamorphic rock. We'll go over the key processes that go on during metamorphism. We will talk about different types of metamorphic rocks, recognizing what we call foliation. We will go through the examples of metamorphic rocks and how they differ from one another. And then we will relate metamorphism to our geologic settings and plate tectonics. And then we'll explain the grade of metamorphism. So understanding what we mean by the grade of metamorphism and what that means for the outcome of the rock. So another review of our rock cycle. We know that magma material can solidify underground, creating an intrusive igneous rock, or it can reach the surface, solidifying on the surface, creating an extrusive igneous rock. Weathering, transport, and deposition of any rock can then create a bed of sedimentary rock. If we have burial, high pressure, and high temperatures of any type of rock, we create what is called metamorphic rock. So that completes our rock cycle, the three types of rocks: igneous, sedimentary, and metamorphic. They can each become each other. So metamorphic rock, the word comes from the Greek word to change form. What that means is a protolith undergoes a solid state change. This is the process of metamorphism. So a protolith is the original rock before it undergoes metamorphism. Generally, metamorphism occurs from burial. Any rock can be buried. Any rock can be a protolith. So any rock can become a metamorphic rock. Any rock can undergo a change in pressure and temperature, compression or shear, to create metamorphic rock. So an igneous rock, a sedimentary rock, or another metamorphic rock can undergo metamorphism and create a metamorphic rock. So here's an example of a protolith, which is a red shale, a sedimentary rock. As it would undergo metamorphism, if it underwent extreme metamorphism, it could create what we call gneiss, spelled this way. So metamorphic rocks, we look at the texture, the minerals present, and the foliation. So metamorphic texture, we see that the grains in the rock have grown in place generally. With minerals, we would only expect to see minerals that can grow under metamorphic conditions, so high temperature and high pressure. And then metamorphic foliation is what we call the alignment of the minerals when they are aligned in stripes or parallel to one another. So usually high levels of metamorphism are going to create this foliation, and we will end up seeing stripes or layering of dark versus light minerals. So we will actually see physical dark and light stripes throughout the minerals. Throughout the rock. So metamorphic processes, there are a few that can cause metamorphism. I'm going to go through some examples here of these 5 that I have listed, but I just want to note up front that metamorphic processes take thousands to millions of years. It is an incredibly slow process, metamorphism. So keep that in mind as I am explaining how these metamorphic processes can actually occur. So for metamorphism, we need high heat or high pressure or really, really intense compaction. Those are things that do not happen quickly. They happen over very, 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 very long time periods. It takes a very long time. So our first example of metamorphism we call recrystallization. So this is where the minerals actually change size and shape. So this is something like firing a kiln or firing potter's clay. So this would be some example. Here is our protolith, so the original rock with its tiny clasts. And then after metamorphism, the metamorphic rock that forms has large new grains. So recrystallization, sometimes you can see similar coloring, similar types of minerals within, but the rock is going to look quite different. There can also be neocrystallization. So neocrystallization is my favorite. This is where new minerals actually form within the rock. So there's new minerals that can form due to this high temperature and pressure. The initial minerals in your protolith become really unstable, the bonds will break, and new minerals are then able to form with that material. So a shale here could become a garnet mica schist, which here is garnet. If you remember, that is the red mineral that often forms with neocrystallization. So under intense metamorphism, you can have a shale rock become what we call a garnet mica schist because it is a schist made up of garnet and mica. A schist is a type of metamorphic rock, which I will get to towards the end of this lecture. So we can also have what we call pressure solution. So this is where mineral grains will partially dissolve if there is a small amount of water involved. So minerals will dissolve where they meet. So here is our protolith, and there are spherical grains of these minerals along the planes where the minerals meet. If there is water going on in this area, then there could be what we call this pressure solution, where in the metamorphic rock, we end up with elliptical grains. So instead of having these spherical grains, we end up with dissolved material from the spherical grains. They become more of an elliptical shape. So this new growth here in between these grains is from the material that was dissolved. So there's some migration of ions to cause these spheres to turn then more into elliptical shaped grains. We can also see something which we call plastic deformation. So this is where the grains in your protolith actually soften. So instead of dissolving and removing this material, like the last example, it's actually that these grains are just softening and then changing shape. So they're softening and then they're being squeezed due to some compression, so they become elliptical. So we're not actually removing and moving any material. It's just that the material, the protolith acts sort of like a plastic where it can be deformed. So it can be stretched and reshaped without actually breaking. So this is what we call plastic deformation. So there's some examples of the type of changes that can occur due to metamorphism. So metamorphism can be caused by many things. The most common are heat and pressure, and they generally do happen together. High compression and shear can often also cause metamorphism, as well as hot water. So we don't need all four of these to have metamorphism occurring, but they generally do happen together, or at least a combination of them. So I'm going to go through each of those examples. So metamorphism due to heat. So metamorphism occurs generally between about 250 and 850 degrees Celsius. This is where there's enough energy from the heat to actually break and reform the atomic bonds within the protolith, within the existing rock. So here is where we would expect to have neocrystallization or recrystallization. Metamorphism due to pressure, and please note that pressure and heat generally happen together. This is where we have rock being buried. So the pressure of the rock is going to increase with depth. So as the rock is buried deeper and deeper beneath the surface of the earth, that pressure is going to increase. So metamorphism usually occurs between 2 and 12 kilobars in terms of pressure. So that is going to be very far beneath the surface of the earth. So that increased pressure is going to cause the atoms to be very, very tightly packed together, creating a much denser material. So this can cause a lot of phase changes or neocrystallization. So here is another example of neocrystallization where garnet grew out of this material due to very, very high pressure metamorphism. So compression. Compression is where we have stress in one direction. So for example, here we have stress pushing inwards from the sides, but not from the top. So here is our card tower. We have air pressure originally that is in all directions, all equal. And then we stomp on it, adding compression, meaning we are pushing in just one direction. We're going to squash that house of cards. So compression is very common where we have tectonic activity. So here's an example of a person swimming. So he has the water pressure all around him in all directions, and then we apply compression when he does or she does her flip turn against the wall, pushing in one direction. So compression can happen at tectonic forces where we have strong force in one direction pushing on the rock. We can also have shear. Shear is a little different. This is where the material moves sort of sideways. So this can cause the material to actually be smeared. So instead of just being squished in one direction like compression, it's actually being smeared out like a deck of cards. So something more like this, taking a round sample and then adding shear, you're going to smear it in one direction. So like you're sliding across that deck of cards. That is called shear, where we have motion in one direction on the bottom and the opposite direction on the top of your rock. So with compression and shear, they are often together. These cause our minerals to change, so they can change shape, but they generally do not break. So we are not breaking our minerals. Here is where we get that change of shape without breaking. So we can go from an equant mineral, which is a round, equal shaped, to what we call inequant or elongated shape. So this often is occurring, or this often causes minerals to rotate and end up in what we call a preferred orientation. So where there is compression, if you look at this example here, there's compression from either side. So this causes the minerals to actually align. You can see that they're long and platy and elongated in this direction. So this preferred orientation or alignment of our minerals due to compression and often shear is what we call foliation. So when you can see a clear preferred orientation or a clear alignment of the minerals within your metamorphic rock, we say there is foliation within that rock. We can see the foliation in that rock. So another maybe a little bit less common type of metamorphism is caused by hot water. So where there's hydrothermal fluid, really, really hot water, and that water has a lot of dissolved ions in it, this can very much accelerate metamorphism. So this would be when a rock can actually change its composition because it comes in contact with hydrothermal fluids, meaning it comes in contact with this very, very hot water. This very, very hot water is also holding a lot of dissolved ions to react with that rock. So next I'm going to go through the different types of metamorphic rock and the grades of metamorphism. So types of metamorphic rock we consider either foliated or non-foliated. So does the rock have foliation, or these parallel lines, these alignment of your minerals, or not? So if it does, we know that there was compression or shear during the formation of that rock. We also know that there is a clear preferred orientation of crystals, and those crystals are going to be inequant. These rocks we will classify by the type of foliation. Non-foliated metamorphic rocks have not undergone compression or shear, and we would expect very equant minerals because there's no compression or shear, and these we would classify by composition. So for our foliated metamorphic rocks, there's sort of a broad classification due to the foliation or the amount of foliation. Our metamorphic rock types and the names that we call our metamorphic rocks have to do with the amount of metamorphism that they underwent. So as the metamorphic grade increases, meaning as the temperature and pressure that formed that rock increases, the rock type changes. So metamorphic grade, we consider the amount of temperature and pressure that rock underwent during formation. So a metamorphic rock that underwent metamorphism, but it was a rather low metamorphism, would be something like a slate. As we increase the amount of metamorphism that rock underwent, the rock type changes. Gneiss, for example, is a very high-grade metamorphic rock. So when you see a gneiss sample, you know that rock underwent very high temperatures and very high pressures, a lot of metamorphism. The parent rock can vary. So there can be many different types of parent rock that if they undergo the same amount of metamorphism, it can become the same type of metamorphic rock. So here's a really nice image showing us low-grade metamorphism, like shale, is here at the top of our image, and then as we increase pressure and increase temperature, we are going to create higher and higher grade metamorphic rock all the way to gneiss, and our very high grade metamorphic rock. So I'm going to go through the main 4 types of metamorphic rock. So a low-grade metamorphic rock would be a shale. Would be a slate. It is usually formed from a shale. So slate is a metamorphic rock. It is usually like a very fine clay. This is the lowest grade metamorphism, but it has a very, very clear foliation that is not so visible in terms of color, but there will be a very, very clear parallel alignment of the minerals, which allows for cleavage and breaking along that parallel alignment. So slate can often be used for roof tiles or for floors or for countertops or black backsplashes, because it's very easy to break it into flat sheets due to the foliation of the minerals. So because slate has such clear foliation, it's very easy to break slate along the foliation to create nice flat sheets. So here is an example of slate being mined, building this nice structure here. Phyllite is the next one. This is, so if slate continues undergoing metamorphism, we might end up with this very fine mica-rich rock. So remember that mica is that shiny sheet silicate that peels off. It could make a window or a cellophane. This is more of a low to medium grade metamorphism. So here is where we have clay minerals neocrystallizing into that mica. So the mica is forming out of that material. So you'll generally see a very shiny surface. These rocks are very shiny due to the presence of a lot of that mica mineral. If we increase metamorphism even further, we will get schist. So schist is going to be much more of a coarse rock with larger micas. So here, maybe this picture is a little hard to tell, but this whole piece here is a bit of mica. This whole piece here is a bit of mica. We have larger grains of mica. So rather than this just looks shiny, like there's glitter all over it, here we can actually point out and often even peel off the pieces of mica within this rock. So this rock has had a much longer time to form that mica mineral. In this, we often see very distinct foliation and parallel alignment of the mica crystals. So you can see here, sorry, it's a little blurry. You can see a little bit here, there is some parallel alignment of that mica along this line here. So schist can also have other minerals that have grown due to neocrystallization. So here is another example of garnet, which is that red mineral that grows from neocrystallization. So a high-grade metamorphic rock we would call gneiss. Gneiss has a very, very clear, distinct foliation. So with this much metamorphism, this rock has been under very, very intense heat and pressure for a very long time. The minerals will actually start to separate into bands. So we would have light bands of our felsic minerals, those light-colored minerals, and then the mafic minerals creating the darker bands. So we'd have really clear lines of felsic versus mafic minerals. So what's happening is during this incredibly high metamorphism, the ions will actually migrate towards each other, creating these very clear layers of light versus dark. So here is another image of that metamorphic grade chart. So as our temperature increases and as our pressure increases with depth, so we're thinking this is the surface of the Earth here, as pressure increases as you go down in depth, we're going from a non-metamorphic rock to a low-grade metamorphic rock at high temperatures, high pressures. As we continue increasing temperatures, as we continue increasing pressure, we're going to get that intermediate grade and that high-grade metamorphism. So those are our foliated rocks. We can also have non-foliated metamorphic rocks. So this would be something like quartzite, which is here, an example here. This is a metamorphized sandstone. We can also have marble. So marble is a metamorphic rock that is non-foliated. It doesn't have clear orientation, clear parallel orientation. It is generally made from limestone. So these two are good examples of recrystallization. So we do not have foliation in these types of metamorphic rock. So now where does metamorphism occur? Metamorphism, remember, we need high heat, we need high pressure, we need compaction and shear. So there's quite a few places that metamorphism can occur. So there's contact metamorphism, burial metamorphism, regional, hydrothermal, subduction metamorphism, and then also shock metamorphism, which is a little less common. So I have a video about the types of metamorphism for you guys.
When existing rocks are buried deep within the earth, they undergo intense heat and pressure, and many times the minerals and the constituents within that rock change into entirely new forms. And those rocks that form through that process are called metamorphic rocks. There's two types of metamorphism that we need to be concerned about. One is what I just described. That's called regional metamorphism. The other is when rocks come in contact with very high heat. Not necessarily at high pressure or high depth, but high heat. And we call that contact metamorphism. I'll give you a couple of examples. Here in the kitchen, we've got a marshmallow, and we've got a nice little butane torch. Now sometimes volcanic lava will come up to the surface and erupt, or just near the surface will come in contact with other rocks that were already in existence. And the heat, the intense heat from that lava, will actually change the rock into something completely different. For example, I've got this marshmallow, which is made of sugar, which has carbon, oxygen, and hydrogen atoms in it, and I'm burning the sugar, which means I'm stripping off the hydrogen, stripping off the oxygen. I'm leaving just the burnt carbon. That's the charcoal, the black stuff that's left behind. So I've metamorphosed that sugar within the marshmallow using the high heat. The same thing happens within rocks that have undergone contact metamorphism. Now, regional metamorphism occurs on much larger scales. We have to take large areas of rock and bury them deep within the earth to generate the heat and pressure needed to get new minerals and new rocks to form. Examples of that happening in nature, if we take a limestone such as this, which forms in a lake or ocean, and we bury it, we may get something like this, which is a marble. And we might make our kitchen countertops out of that stuff. Or we may have a sandstone like this, it's very quartz-rich, and bury it deep within the earth, and we may get a variety of different rocks, from slates to schists, which have laminations and little foliations within them. We may get new minerals, such as these garnets, which grow, and eventually we'll form very coarse-grained rocks, like schists, gneisses. Gneisses are very coarse-grained, often banded and foliated. So we get brand new sets of rocks, and a good example in the kitchen of this would be one of my favorite foods, lasagna. Matter of fact, I was just cooking this morning, and just so happened to have a nice cheesy lasagna. What's interesting about this lasagna is it's a pretty good example of a metamorphic rock. The initial constituents we put into the lasagna were pasta, cheese, tomato sauce, different types of cheese that actually changed form while we cooked it under high heat. Now, we don't have pressure in the oven, but we do have heat, and those things melt and they all congeal to form this new food, which is like regional metamorphism in a way, although the pressures are much lower in the oven, but it's a pretty good analog, and it tastes good too.
Now that we're all hungry for lasagna, let's go through some examples of these types of metamorphism. I like any time that you can relate geology to food. So contact metamorphism, like he said, this is when your metamorphic rock is coming into this is when your rock is coming into contact with very, very high heat, generally from magma. So this is going to actually create different zones or different layers of metamorphism. So right up against the very, very, very hot Pluton, you will have your high-grade metamorphism, and then as you move away from the heat source, you're going to go from higher grade to lower grade. So you'll actually have this sort of fading out effect due to the change in temperature from the incredibly hot Pluton away, outward. So you'll have lower grade metamorphism on the very outer edge. You can also have burial metamorphism. So as you bury sediments over time, the temperature is going to increase. As you bury, the pressure is going to increase. As time goes on and that burial becomes very, very deep, it's going to start getting closer to the center of the earth. The temperature is also going to increase. You're going to have metamorphic activity begin. Regional metamorphism, so this really is where we have tectonic collisions or continental to continental convergent zones where we have mountain building. So this, we have a large amount of heat, a huge amount of pressure, and a lot of compression and shearing due to this enormous pressure of the convergent boundaries. Remember that continental to continental boundary, neither of those plates will be able to subduct. So that is collision, where we create huge mountain ranges and a lot of metamorphic activity. Hydrothermal, so this is where we have the addition of very, very hot and also chemically aggressive water. So we have really, really hot water that has a lot of ions in it. This is generally at the mid-ocean ridge. So at the mid-ocean ridge, where we have magma reaching the surface, there's going to be incredibly hot water from right there at that surface. That water is going to have a huge amount of extra ions. That water is going to help increase the metamorphic activity there. Subduction, we know all about subduction. Subduction can cause metamorphism at the trench area. So where we have this trench forming, because we have here our oceanic crust subducting underneath our continental crust, we know that the continental crust is going to dip a little bit, creating a huge a huge trench. There can be really, really high temperatures and pressures right there where the two rock types meet. So we can often create a very specific type of metamorphic rock that is called blue schist. So blue schist generally forms when we have incredibly high pressures and not quite as high of temperatures. And then shock metamorphism, I want to mention because it's kind of fun. Doesn't happen very often, but this is where kinetic energy transforms into heat in the form of something smashing into the earth. So for example, a meteorite hitting Earth, we would melt or vaporize the rock almost immediately. This would cause extreme compression of a meteorite hitting the Earth. This would cause quite a bit of metamorphic activity. So a crater, for example, would have a lot of metamorphism around due to that shock impact, that shock metamorphism. So remember metamorphic grade. Low grade is really weaker metamorphism. As the metamorphism increases, or as that rock undergoes higher temperatures and higher pressures, the grade of metamorphism is going to increase. So you can't just create from your protolith a very high grade metamorphic rock. You're going to start with your non-metamorphic rock. It is going to start as a low grade, like a shale, like a slate, and then it's going to increase in metamorphic grade. So that rock will go from a slate to a phyllite, a schist, to a gneiss. So you can't just start right at a gneiss because the rock must increase in temperature and decrease in pressure. So it will actually move through all of the grades of metamorphism. So metamorphic rocks often will reflect our plate tectonic setting, so we can tell by the type of metamorphic rock where that rock was formed. So this is a really good summary slide here, explaining where we find each type of metamorphism: contact metamorphism, hydrothermal metamorphism, burial metamorphism, for example. So where do we actually see metamorphic rocks on Earth? We do see, well, I should say, where do we see metamorphic rocks at the surface? So when we see large, very, 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 very old areas of high-grade metamorphic rock that is now at this point exposed, we call that a shield. So there are some continental interiors. For example, we have the Canadian Shield in North America. This is a very ancient high-grade metamorphic rock that at this point now is at the surface. So everything has been eroded away that was on top of it. So it has been brought to the surface. That is called exhumation, where very deeply buried rock ends up at the surface because everything else on top of it has been eroded. So this metamorphism, it happens deep underground. It has to be very high pressures, very high temperatures. So how do we ever see it? We have to wait. So over millions of years, everything on top will be eroded to the point where we do actually see metamorphic rocks at our surface. So metamorphic rocks that we see at our surface, we can assume they are quite old, like all of the shields that we have on the surface of the Earth today. So, fun fact, California's state rock is actually a metamorphic rock. So it is iron-rich rock. It is made of a lot of sheet silicates, and it is a very low-grade metamorphic rock, and it's formed by hydrothermal metamorphism in our ocean crust. So it is very common in central and northern California. We don't have it so much occurring naturally down here in southern California, but it is a low-grade hydrothermal metamorphism, and it generally has a greenish-bluish tint.